Let's understand atomic spectra.
All right, Gumarazad, let's break it down. The atomic spectrum is basically the unique set of fingerprints an atom leaves when it interacts with light. When electrons in an atom absorb energy, they jump to higher energy levels. When they fall back down, they emit light at specific frequencies. Those frequencies form the atomic spectrum. Each element's spectrum is distinct, which is how we can identify elements in distant stars or even in a lab.
That's so small. These things are working on a very small scale. Can you give the exact number at which this is working?
Absolutely. The energy levels in atoms are separated by very specific amounts. For example, in the hydrogen atom, the visible lines in its spectrum, the Balmer series, correspond to transitions where the electron drops to the second energy level. The wavelengths are in the range of a few hundred nanometers. For instance, that famous H alpha line is at about 656 nanometers. So, yes, we're talking tiny wavelengths.
But how do we capture that wavelength that is being emitted? Okay, you are also mentioning that the transition is happening, and during the transition, the release of energy in the form of wavelength.
Exactly. When an electron transitions from a higher energy level to a lower one, that energy difference is released as a photon, basically a particle of light. Now, to capture that wavelength, we use something like a spectrometer. A spectrometer essentially splits light into its component wavelengths, like a prism. Each wavelength will show up at a different position, so we can identify exactly which transitions and therefore which elements are present.
What do we so what are the first attempt to understand this atomic spectra?
The earliest attempts go back to the 19th century. Scientists like Fraunhofer noticed dark lines in the sun's spectrum, but it was Balmer in the 1880s who found a mathematical pattern in hydrogen's visible lines. Later, with Bohr's atomic model in 1913, we finally understood those lines corresponded to electron transitions. This was key, linking observed spectral lines to quantized energy levels. In short, the journey began with careful observation of light and patterns long before quantum mechanics explained it all.
Okay, what did Fraunhofer observe? Like dark line in the sun spectrum. So first of all, how they get the sun spectrum? And okay, basically sunlight is coming and then they capture that. And
Exactly. Sunlight, when passed through a prism or diffraction grating, spreads out into its spectrum, like a rainbow. Fraunhofer did this in the early 1800s, using telescopes and prisms to carefully analyze the sun's light. What surprised him were these dark lines, now called Fraunhofer lines, where specific colors or wavelengths were missing. We now know those are caused by elements in the sun's atmosphere absorbing specific wavelengths. So Fraunhofer essentially captured sunlight and revealed it had a hidden code.
okay, okay, you mentioned about they are thinking about the sun spectrum and how did they observe something different in that case?
What Fraunhofer noticed was that the sun's spectrum wasn't a continuous rainbow. There were thin, dark lines breaking it up. These lines meant something was absorbing certain wavelengths before the light reached Earth. At first, they didn't know why. Later, it became clear. Elements in the sun's atmosphere, like hydrogen, sodium, and iron, were absorbing their characteristic wavelengths. Those missing pieces in the spectrum were like clues, and over time, scientists decoded them, linking each line to specific elements, thus identifying what the sun and other stars are made of.
No, basically the sun spectrum that we are getting actually the chemical reactions inside the sun's core, whatever things are there, but uh, the transition element that from one state to another state inside such elements like hydrogen, sodium, or something. That also that kind of frequency added to the spectrum that they found that was different from the general spectrum.
Yes, exactly. The light we get from the sun is produced deep inside, mostly from nuclear fusion in the core. But before that light escapes, it travels through the sun's outer layers. Atoms in those layers, like hydrogen, helium, sodium, absorb certain specific frequencies. When those electrons jump up and then fall back down, they emit light, but not necessarily in the exact same direction. So, by the time that light reaches us, some of those wavelengths are missing. That's what gives us those dark absorption lines in the sun's spectrum. Each element leaves its own fingerprint, which is how we know what's out there, even if we can't directly touch it.
So this electron jumps up and then falls back down. They emit light. Okay, so during that, did they lose energy? I mean to say that electron is being occupied to its initial ground state again, but during the transition, they emit something. That is what the extra thing that they captured.
Exactly. When the electron falls back down, it releases that energy as a photon of light. The photon's energy, and therefore its wavelength or color, matches the exact difference between the two energy levels. So, yes, the electron returns to its lower, more stable state, having lost energy in the form of emitted light. When we capture that light, we see those distinct wavelengths, giving us the spectrum. So, what's extra is that specific energy being released as light, and it's what we measure in atomic spectra.
What about the violation of conservation law in this case?
Actually, there's no violation of conservation laws here. Energy is conserved. When the electron absorbs energy, it moves up to a higher energy state. And when it falls back down, that energy is released as a photon. The total energy before and after remains the same, just redistributed. Similarly, momentum is conserved too. The atom recoils slightly when emitting a photon, balancing the momentum. So everything stays conserved, just transformed between light, atom, and electron.
So what about so basically the extra energy that atom needs to excite that is coming from external, that is what the thing is. Nothing is changing at that scale.
You've got it. That extra energy to excite the atom typically comes from an outside source, like a photon of light or an electron collision. Nothing breaks the rules. The atom absorbs energy to excite its electron, and when the electron returns to its lower energy state, it releases that energy again, usually as a photon. It's a perfect give and take, just shifting energy around as nature loves to do.
So when they excite atom, why they only excite the electron? Why not they excite the protons or neutrons? Because there are many things now.
Great question. The reason is that electrons are much less massive and are bound by electromagnetic forces, which means they can easily absorb photons with typical energies, like visible light. Protons and neutrons, on the other hand, are held together by the strong nuclear force and require vastly more energy, like gamma rays, to excite them. In everyday thermal or visible light conditions, electrons are the easiest energy sponges. That's why atomic spectra mainly come from electrons making those jumps.
So, till now we have discussed about this Fraunhofer thing. What next? The things that capture that information, like this hydrogen atom in the visible line spectrum, the Balmer series. Can you explain that again? Now, Fraunhofer sees something that Balmer explain it clearly.
Sure. So Fraunhofer first saw those dark lines, but didn't know why they appeared. Decades later, Balmer focused specifically on hydrogen. He discovered that the visible lines of hydrogen had a pattern. In 1885, he found a formula that described the wavelengths of these visible lines. In other words, Balmer mathematically explained why hydrogen emits light at those particular colors. Later on, Bohr's atomic model explained this even deeper, showing that these lines come from electrons jumping between quantized energy levels. So Balmer gave us the math pattern behind hydrogen's visible spectrum, tying it all together.
So we have found a formula that describes the wavelength of those visible lines.
Exactly. Balmer found a simple mathematical formula that predicted the wavelengths of the visible lines in hydrogen spectrum. It said that these wavelengths depend on integers, whole numbers, and a constant. Later, it became clear that these integers represent electron energy levels. Balmer's formula fit the pattern for visible light, and then Rydberg extended it to cover all hydrogen transitions. In short, what started as a pattern became a doorway to understanding quantum energy levels.
This hydrogen transition is still useful in modern physics application based thing, like still it is correct, the transition that they have calculated in the form of waves, probability and all those abstract notion.
Absolutely, it's still correct. Those transitions are fundamental to quantum mechanics. The energy levels Balmer identified are explained by the quantum theory of the hydrogen atom. Today, we still use them in applications like atomic clocks, spectroscopy, and even in understanding stars. Quantum mechanics refined the understanding. Now we talk about wave functions, probabilities, and so forth, but the actual energy transitions are the same. So, from 19th century observations to cutting edge tech, hydrogen's transitions remain essential.
So what about those uh, the hydrogen atom has subcells, or like there are in atomic structure every element has orbitals like theory. So how does this transition affect that? Okay, also we there talked about S2P transition and many things related with that, no?
Yes, exactly. In hydrogen, we started with the simplest picture, just one electron jumping between energy levels. But as we build up to more complex atoms, those energy levels split into sublevels called orbitals like s, p, d, and so on. Each orbital has slightly different energies, shapes, and angular momentum. Transitions now happen not just between principal energy levels, but between sublevels. For example, in more complex atoms, you get transitions like from a 2s to a 2p orbital. The same principles apply, energy differences determine the photon emitted or absorbed. So while hydrogen gave us the foundation, multi-electron atoms add richer layers of complexity, but still follow the same quantum rules.
So this was a very little discussion about spectra. Can you give some conclusion what we have discussed till now so that I can end this talk?
In short, we started with Fraunhofer noticing dark lines in the sun's spectrum. Those lines were elemental fingerprints. Balmer then found a pattern for hydrogen's visible lines, leading us to understand that electrons jump between quantized energy levels. That foundation still holds today. In modern physics, we've expanded from hydrogen to complex atoms with orbitals, yet we still use these transitions in everything from spectroscopy to quantum tech. In essence, we've gone from simple observations to a full quantum understanding that's as valid now as ever.
Okay, thank you.